Let us continue to talk about different probing methods in the hash table. In our previous video, we looked into the linear probing. So basically, we use the I to control where are we going to look away from the home position. When I equal to 0, indicating the first time of the try, it is the home position that you will look into. When I goes to 1, you look into the next location. When I equals to 2, you go to 2 positions later. We discussed about the problem that it may occur is that it can form the clusters, and the cluster will possibly join with another cluster to reduce the performance. And therefore, in the quadratic probing that we want to look into, use a little bit more sophisticated way of controlling the I. So let's take a look of the quadratic probing. In the quadratic probing, you can see that when we try to do h of k and I, it's the same thing with h of k, which is the way you try to find a home position plus a constant parameter multiplied by I plus another constant value multiplied I squared. And then you can see that it's basically very similar with the linear probing, but a little bit more complicated. However, you can see this. If we put C1 equals to 1 and C2 equals to 0, when 0 multiply I squared, it will always get a 0, indicating that you don't need to care about the I squared part. Then it's basically the same thing with the linear probing. Of course, if we try to put C1 equal to 0 and C2 equals to 1, which is the example that we want to look into, then we use I squared to control the positions away from the home position. Let's take a look of what's happening here. So basically, you can see that if we use the same operation, similar operation, I modify one small part, and we will be able to look into that later. And we try to use the quadratic probing. At this time, we try to say that we set C1 equal to 0 and C2 equals to 1. And therefore, the whole quadratic probing will become h of ki equals to h of k plus I squared. Because C1 is 0, we don't need to care about this one anymore. C2 is 1, which indicating it is I squared itself. So what is going to happen here? This is what I have summarized for you guys. You can see that for the home position, if I equal to 0, then you will plus 0 squared, which is the same position of the home position. If it is occupied, I change to 1, what you will see is that you will become I squared, which you will look into the next location. If that location is already occupied, then instead of look into the 2 position away from home position, it will change into I squared, which is 4, saying that that's 4 spaces away from the home position. And you can see that it will be able to make you jump more gaps when the I is still failing. When I goes to 3, you look 9 position away from the home position, and 4 and 5, and you can go up to a large number to make sure you will be able to quickly walk over the cluster if there is one over there. And therefore, this is the idea of the quadratic probing. Let's try to take a look of the action and see what's happening here. So you can see now when we try to store the value of 9, it's the same operation. H of 9, 0 equals to h of 9, which will give you the operation finding the position equals to 1, home position, and then because I is 0, so I squared still give you the value of 0, and therefore you look into the home position, it is available, so we can put 9 over here. While we try to look into the next value, 21, we feed the 21 0, and then you will look into the home position of 5, and finding it's available, so number of probing equals to 1. Now, if we try to look into store a value of 17, what's happening is that it will look into the home position, which is going to be the value of 1, and finding out it is not available, and therefore you will look into I change to 1 position, which is 1 place away from the home position, and therefore you will look into the space of 2, because 1 multiply 1 squared, which is the I value, equals to 1 basically, and so you look into the next location, finding it is available, and therefore number of probing equals to 2. While we try to store the value of 18, it will first look into the home position, which is 2, and then you will look into the next location, because when I equals to 1, you look into the next location, finding out it is available. So we can put 18 over there, and then number of probing equals to 2. So now let's see this. If we want to store the value of 82, well, 82 home position for 82 is going to be the location of 2. Of course, it's occupied, and you will see that when you try to look into the next location, it will look into index of 3, because when I equal to 1, I square equals to 1 as well. So you will find out it is occupied, and therefore instead of looking into the next location like linear probing, it will look 4 spaces away from the home position. So you will look into 1, 2, 3, and 4, finding this is the available location to store the value over there. Let's see this. So you can see that when h of 82 0, you will look into the home position, finding it is occupied. And then when you change I equals to 1, you will look into the next location, which is occupied. So now when we change I to 2, you will multiply 1 multiply 2 square. And basically you will get 4 positions away from the home position. That's why you can get 82 over here. When we try to do the deletion, it's the same thing. We try to use the same equation to help us finding the value. You will see that 9 is over there. Basically, it will tells you that it is there. To delete that, you need to leave a special sign out of it, and therefore we will be able to do that easily. While we try to store the value of 80, because it hits the home position of 0, so we have no problem finding it. While we try to store 32, you will do home position equals to 0, and now you need to look into the next location, because index of 0 is already occupied, and therefore you look into the next location, finding 32 is available to put in here. There was something here before, but it is available now. The last one is a problematic situation. I want you guys to see this. For the last one, when we try to do the delete of 81, what is happening is that it will look into the home position, finding out 32 is not 81, so I'm not able to delete it. By the way, you need to understand that 81 does not exist over here, so that we need to find a location that is indicating a null, and therefore we will be able to understand that the value is not there. We need to keep searching until we find a null value. However, you see that when we start looking into the first location, home position, which is index of 1, finding it is not 81, so you need to look into the next location. And this one obviously is also not 81, so you need to look into 4 positions away from the home position, 1, 2, 3, 4. So you will finding out that's also not available, and then you need to look into 9 positions after that, so 5, 6, and of course wrapping around 7, 8, and 9, hitting this spot again, you will see an operation that keep going back and forth. So you can see that 81 is hitting here, 81 is hitting multiple locations, but it's the loop over there. If we look into the operation, you see that originally the index home position gives you the value of 1, and then we look into the next location, which gave you index of 2. That's what the 81 in the first 81 in index of 2 happens. And then when we look into 4 positions away from the home position, we will look in here, finding out it's still not 81. And then we need to keep going. The next one hits the index of 2, so that's where the second 81 appears in the index of 2. And then we move to 4, which will give you 16 places away from the home position, finding the index of 1. That's where the second 81 comes in. You can see that we will be able to do a lot of these iterations, and to my understanding, you will hit a deadlock that you will keep going and then not able to find the 81, but it's still keep moving. This is something I want to discuss with you. I want you guys to understand why is it? Why does this happen? Basically, a situation like this happens because we only have 8 positions. Out of those 8 positions, 6 of the positions are already occupied. And that's why the performance of this hash table is not doing well. There's too many places are already mapped. In terms of this, you need to increase the size that you created. And therefore, when you try to do, no matter it's insert, delete, or search, you need to put a mechanism saying that under certain circumstances, if I look for 10 locations already, and I'm still not finding any solutions out of it, there is a possibility that we use too many spaces. And that's something I want to discuss with you guys to make sure you understand the performance versus the spaces that you are able to create. Like we discussed in our earlier discussion, if we can create unlimited amount of space to map everything, then we don't have all of these collision problems. The only problem is that we don't have that many resources. That's why we want to reduce the resource, but we also want to maintain enough spaces to make sure that collision only happens once in a while, and we have big enough space to handle all situations.